Hi everyone. I would like to get through today slides 51 through 61. So we're going to do 10 slides today in class. And then I wanted to give you the rest of your class time to work on that chapter 6 packet of multiple choice questions. As you're doing those, and if you want to do those in your group, or you kind of want to do them together as a class, then that's fine. And if you have questions, then you can just email me, and then I can email you right back, or you can post on the blog and I'll email you right back tomorrow, because I'll have my phone with me all day long. So remember that on Saturday morning, I'm going to post a video for homework, and then we'll start on your PowerPoint, or on your video for homework. We'll start at slide 62, and we'll get through maybe 15 slides, and then we will have very minimal slides to go through on Monday, so then hopefully we can just spend Monday as mostly like a review for your multiple choice test, which is going to be on Tuesday, just as a reminder. So I want to go back to the photoelectron spectroscopy, or especially this photoelectron spectrum. This is where we ended in class today, and I had you write down an explanation, kind of explaining to me why I would see the 1s peak at 870 for the energy, and then why I would have the 2s peak for neon at 48.47, and why the 2p peak is at 21.61. But let's just go back and again kind of talk about what photoelectron spectroscopy is. And we said that photoelectron spectroscopy is where we have, it's really an application, which I don't think we said today, it's really an application of the photoelectric effect. And we know that the photoelectric effect is where we have light that we shine on a clean piece of metal, and if light absorbs, or if the metal is absorbing this light, it's really the electrons that are absorbing that energy from the photons or from light. And they can become excited, and they can also be emitted. The metal can emit them from the surface. So this photoelectron spectroscopy instrument or spectrometer is going to work in a similar way, in a similar technique. So we have photoelectrons that are escaping, and we're collecting them in a vacuum, and then we have this detector that's going to measure their energy and then measure intensity. So intensity meaning like how many electrons do I have that I'm counting in that detector, and then again measuring the amount of energy. But what kind of energy is it measuring? That's a big question. Specifically when we're thinking about a photoelectron spectrometer or photoelectron spectroscopy, we're thinking about something called binding energy. And binding energy is the energy required to disassemble something that's a whole into its separate parts or into its components. So let me say that over again so we can write that down. This photoelectron spectroscopy technique is really measuring binding energy, B-I-N-D-I-N-G, binding energy. And that is the energy required to disassemble a whole into its components, or taking the big picture and breaking it down into all of its parts or its pieces. So this would be like, I want to think of an entire atom, and then if I disassemble that atom, that would be like removing electrons one at a time until I get stripped away of the electrons and I'm just left with the nucleus. So that would be like taking that whole atom with electrons and nucleus, taking it apart piece by piece, or removing one electron at a time until I just get to the nucleus. So it's kind of something similar there. So in terms of this now is energy, thinking about it in binding energy. Now we said that 870 would have been our 1s peak. And the reason that we see that as the 1s peak and this is the 2s peak, there are a couple reasons that we could see that. There's a huge gap in energy between the 870 peak and the 48.47 peak. So that's a big indication right there that I'm going from energy level of 1 to energy level of 2 here. And then if we know that neon goes 1s, 2s, 2p, the 2s and 2p should be close in energy level, and I see that here. So that's another good indication that the 870 would be 1s, 48.47 would be 2s, and then 21.61 would be 2p. Now, in terms of binding energy, this x-axis, if I'm thinking about the amount of energy it would take to disassemble the 1s electrons from the nucleus, it is going to take tons of energy to get those electrons to move away from the nucleus, because that is that first energy level, which we said is ground state, and because of Coulombic attraction, it has the shortest distance between that energy level and the nucleus. So the attraction is super strong. So it would take tons of energy to remove those electrons away from the nucleus, again, because of Coulombic attraction. So the binding energy there would be very high. Versus for 2s electrons, they're farther away from the nucleus, so it's not going to take as much energy to remove those electrons because they're farther away from the nucleus. So the Coulombic attraction there would be weaker. And then even more so for 2p. Now again, in terms of intensity, I know that the 21.61 peak is a p orbital peak, or I know that that would be the 2p peak, because I know that p orbitals can contain up to 6 electrons, and for neon in this case it will contain all 6 of those electrons. So the intensity, or the amount of electrons in the p orbital, would be more than the s orbital, which I see these s orbitals are pretty much the same in height here. And if I would compare that, the p orbital should be 3 times the size, since I'm comparing 6 electrons to 2, and I pretty much see that with the height of those peaks. Okay, so now I want to go on to chapter 7. And chapter 7 is all about periodic properties of the elements. So this is going to be talking about periodic trends, and then also talking about like development of periodic table, and then families of the periodic table. So like alkali metals, alkaline earth metals. So a lot of this stuff too, guys, is going to be reviewed. So that's why we can kind of go through it, I think, pretty quick. So in terms of development of the periodic table, we started off, or we give credit to Mendeleev for coming up with a periodic table, or arranging the periodic table in a specific way. Now, we know that the periodic nature of the periodic table comes from repeating patterns. So like, we know now that the alkali metals all have similar properties, right? Like, we know that they have 1 valence electron. We know that they react very violently with water. We know that they are soft metals and could be cut very easily with a knife. Those are just properties that all of them kind of share in general. So they kind of have like a repeating pattern in terms of properties. They also have a repeating pattern in terms of electron configurations, right? Like if we think of alkali metals, lithium would be 2s1, sodium would be 3s1, potassium would be 4s1. So same orbital, s orbital, and they have 1 valence electron there. The only difference would be that we're adding an energy level. So electron configurations there are pretty much the same in terms of a repeating pattern. Same thing with properties. So we know that elements in the same column contain the same number of electrons in their valence orbitals, and those are the ones that we know that are involved in bonding. So as the number of known elements increased, scientists began classifying these elements. So we wanted to group them according to their properties. And we noted, or Mendeleev noted, that as he grouped these into similar chemical and physical properties, he found that he was actually arranging the periodic table in terms of atomic weight. So Mendeleev originally ordered the periodic table by atomic mass or atomic weight. But we know that that's incorrect. We know that's not the way that it's arranged now. But back then, that's how he had arranged it. And gallium and germanium. So we have Ga and Ge, gallium and germanium. Those were two unknown elements to Mendeleev, but he could correctly predict their placement on the periodic table, and he did. Now, he had a couple problems though, because he arranged his by atomic weight, and there were a couple elements that don't necessarily go in order based on their weight. So that kind of created an issue. And it wasn't until 1913 that a scientist named Henry Moseley, remember Moseley? Henry Moseley developed the concept of atomic numbers. And we know that atomic number just means number of protons. And he found this atomic number when he bombarded different elements with high energy electrons. And each element could produce X-rays that had a very specific or unique frequency. And then he found that that specific frequency for that element generally increased as the atomic mass did. So generally, not all of them did, but for the most part, as my frequency increased, so did the mass. So he arranged the frequencies in order of assigning them some type of whole number. And that whole number is the atomic number that we use today. And then he said that this atomic number actually corresponds with the number of protons that are in the nucleus of these elements. So for him, these atomic numbers he identified correctly as number of protons. There were problems with Mendeleev's, like we said, periodic table. And we said that, for example, like not all of them increase by atomic weight. So problem with Mendeleev's was argon has a greater atomic weight than potassium. Yet the chemical and physical properties of argon are more like neon and krypton than they are sodium and rubidium. So there were some problems or some holes in Mendeleev's versus in Moseley's, his fit perfectly where those elements should have been placed. So Moseley's studies made it possible to identify the holes in the periodic table. And then that led for us to discover previously unknown elements. So because of Moseley figuring out this atomic number, and then figuring out that those were really just the number of protons, and then rearranging Mendeleev's periodic table, that's where we got our current periodic table today. Now, we're also going to talk about periodic trends. So remember, Mendeleev really was given credit for kind of laying out foundationally the periodic table, and he did so by atomic weight. But Moseley in 1913 comes along and arranges it by atomic number or number of protons. And again, Moseley did that by bombarding different elements with high energy electrons. So as he's bombarding these elements are producing X-rays at a certain frequency. And he found that in general, as the atomic mass or atomic weight is increasing on these, then I'm getting a higher and higher frequency. And so he just gave those a whole number, and then he found that those whole numbers that he gave them were equivalent to the number of protons. So that made the periodic table arrangement perfect versus Mendeleev's, which had holes in it. So now periodic trends. We're going to talk about a couple different periodic trends here. So we're going to talk about atomic radii, so like size of the atom will be one trend. We're also going to talk about ionic size, that will be a second trend. Ionization energy will be a third trend. A fourth trend we'll look at is electron affinity, and of course we're going to also, which isn't listed on here, we also want to explore electronegativity because we did that one also in the past, so we want to look at that one too. In terms of things that can affect these periodic trends, so what has an effect on atomic size, or what has an effect on atomic radii? What has an effect on ionic size? What affects ionization energy? So before we talk about those trends, we have to talk about what can affect them first. Some of the effects in terms of these trends are something called the effective charge of the nucleus, which we have called nuclear charge in the past. So effective charge of nucleus or nuclear charge. We also have subshell electron repulsion, and we have orbital electron repulsion. So we can think about these as like shielding and energy level also coming into play. So let's talk about first effective nuclear charge. Now, in